Okay, so last time we talked about the determinant, and the very end of last time we came up with a determinant formula for an arbitrary size matrix. Well, we did it for a 4x4, but since not everyone here has done induction, I'm not going to do the proper proof for an n by n. But it looks a lot like the 3x3 formula, right? This is what the 3x3 formula looks like, but instead of an n, there was a 3. And remember that last time we, to kind of make the formula a bit, look a little nicer, we substituted this whole expression for just this capital A, ik, which is called, remember, the cofactor. The cofactor of the element A, 1k. So before we go on to talk about maybe the determinants in for different rows and columns, can anyone guess what the determinant of a 1x1 matrix is? So what does determinant mean? Let's start there when trying to figure out this. Yeah, it is going to end up being the number itself. So why do you expect that? Like, based on what we've talked about, like what does determinant mean so far? Like, what do we use determinant for? There are other uses for it, but we've only talked about one use. Yeah, and what determines if a matrix has an inverse based on the determinant? Yeah, so if the determinant is what, then it has an inverse. Not 0, yeah. Okay, so a number. What is the inverse of a number? Let me ask this. What's the identity matrix for a 1x1? Right, it is going to be the reciprocal, yeah. Yeah, while we're here, what's the identity for a 1x1? What does the matrix look like? It's silly calling them matrices, right? Because they're just numbers, right? So what if the determinant of a number is equal to 0? What does that imply? That implies that A inverse doesn't exist, right? Yeah. What is the only number that whose inverse doesn't exist is 0. So it's very intuitive, right, to say the determinant of a 1x1 is just the number, right? The only 1x1 matrix that doesn't have an inverse is 0. So now when doing the determinant of an n by n, right, can you say what part of the formula doesn't work, doesn't make sense? Like, what part of this formula doesn't make sense for 1x1? Like, for example, yeah, the M11. So we could say the determinant of A is equal to the sum of k equals 1 to 1, where it's a very boring thing of -1 to the k plus 1 A11 det of M11. But sum doesn't matter since it's only one term. But yeah, what is M11? So this is not a real thing. What is M11? Yeah, how do we describe the big M? What's the construction of the big M? right. So first row, first column, delete. But yeah, then we have an empty, you can say an empty matrix. Exactly, what is that? So M11 is like the empty set or something. Yeah, so that's why we can't really use that formula for a 1x1. So we have a separate account for thinking about the determinant of a 1x1. Essentially, you just ignore that. So it's not to say that the determinant of the empty set is 1 or anything. Why do you need a formula for 1x1? A couple of things. Later, when we might not get into this class, but when thinking about the determinant of a n by n matrix, you might want to consider, well, as we've been doing here, we can think of determinants of smaller size matrices, and sometimes you might want to think of the determinant of like a single entry, or maybe other things would be like 2x2, and maybe other entries would be 3x3. So we still should talk about it. But yeah, for right now, maybe say the only reason why I want to talk about it is to give an exhaustive definition for determinant, so that which would allow for 1x1 matrices. Yeah. And it satisfies our definition, right? It's if the determinant is 0, then inverse doesn't exist, which is satisfied. Okay, so I'm not going to go through the proof because it's long, and it's something you might see if you take linear algebra like 260. You might see the proof of this, but it's kind of far too tedious to talk about right now. But it turns out that I can kind of give a general idea of it, but cofactor expansion, so how we've constructed it, the cofactor expansion was just on the first row. So you would take the elements in the first row, and you take the minors of the elements in the first row, and have this -1 business over here. So, but it turns out that you don't need to only use elements in the first row, but any other row will work, and the formula will work the same. So, and here's kind of a general idea of why that you might expect that to be true. So when we first did the formula of the determinant, we started out by deleting the entries in the first column and looking at the one less dimension matrix and noticing relationship with the determinant there. Even in our 3x3, that's how we constructed it. But remember that we wanted to say that this has an inverse, or the whole matrix has an inverse. This has an inverse if this little mini matrix has an inverse. Right, that's how we constructed the 3x3 argument. But it's fine, maybe if I wanted to do this, right? If I deleted the elements in like this column, let's say, and I looked at this n-1 times n-1 matrix, right? Would you also agree that the determinant of the whole matrix is dependent on this being a row equivalent to identity? But that would still be something you would need, right? The reduction may look different than what we've done before. Does that make sense? Like, we don't always have to reduce this way. That's just the way we've been doing it. Another example would be, we could have done like this. And then if this is row equivalent to identity, then the whole thing would have an inverse. So we don't always have to use the first row. We've just been doing that because that's more, that's easier to do in our Gauss-Jordan elimination and everything else. But it is not like the only way, to solve these matrices or to row reduce. You can, put their, instead of upper triangular, you could make it lower triangular, for example. So there's a lot of different ways you can, because there's a lot of different ways you can row reduce that. It doesn't matter if you use the first row. You can use any row to reduce, and looking at these smaller matrices, and also for any column. We have column operations, so maybe you'd expect it to be true for any column. So the formula is exactly the same, where instead of I equals 1, for example, if you replace I equals 1, that's the formula we had before, but this is using any row I. So the only thing to watch out for is that the -1 is a bit different. That instead of, so the -1 in our cofactor for the first row is always to the power of k plus 1. So to have that marry with our formula here, the -1 factor will be to the sum of the coordinate. So the -1 will be -1i plus k, and then ai k determinant of mik. So so all of the IKs. So so let's do an example of maybe why we want to use different cofactors. So I'll do an example. Let's do let's find the determinant of this. So now, based on this definition of the determinant, so you have -1 to the I plus k aik determinant of mik. Which row would be preferable to calculate the determinant if you want to do this quick? So which row has the easiest elements to work with? The second row, yeah. And why is that? Yeah, the main things are, you have these zeros here. So those terms, so, right, we have a21 and a22 equals 0. So those terms go away. So that means the determinant just ends up being -1 to the 2 plus 3, a23 determinant of m23. Does that make sense? So let's do that. So what is -1 to the 2 plus 3? -1, right? Because -1 to the 5 is -1. What is a23? That's just our entry here. And then someone give me m23. Give me the first row, yeah. 1, 2, 1, 1. And again, you delete the third column and the second row, and what's left over is 1, 2, 1, 1. Okay, let's calculate that. What is the term of this? That is subtraction. At 1 minus 2, so -1, so it's equal to 1. To see how in the if you expand on the first row, you would have three different terms, right? You would have 1 times 0, 1, 1, 2, minus 2 times 0, 1, 1, 2, and then plus 3 times 0, 0, 1, 1. Right, so that if you calculate this, this will also equal, but of course there's a lot less to do in the first way we did it. Okay, any questions on that one? Okay, so let's do another one. Okay, so what row or column would be best here? Second column, good. Okay, so let's use the formula for the column cofactor. So negative, so it would be A K I and determinant of M K I, or maybe we can use J because we've been using J for column. So it'd be K plus J. Yeah, the -1 is I plus K, and then it's 2 plus 3 because that's this one. Yeah, so for here, yeah, what is the only entry? Only A22 is not equal to 0. So that means we can do -1 to the 2 plus 2, A22, determinant of M22. Okay, so what is -1 to the 2 plus 2? Okay, yeah, that's 1, and A22 is 1. And someone give me the matrix. Yep, 1, 1, 1, 2. All right, that is deleting this column and this row, and we're left with 1, 1, 1, 2. The M thing. Explain how that works.
Yes, the M thing.
Yeah, so M22 is the matrix from deleting the second row and the second column. The row is determined by here, and then the column by the second number. So here's 2, 2, and now let's eliminate the second column and the second row. So what's left over is we have a 1 in the first row, and then 1 and a 2 in the second row. That's what's left over. Right, you omit that second column and second row and like squeeze the matrix down. Yeah, so this is M22. Okay, great. That's better? Okay, so the determinant of this 2 by 2 is 2 minus 1 is equal to 1. So that's also. So again, just realize that if I picked the second row to expand on, I would have a lot more things to worry about. Okay, so questions on that? Okay, let's do a 4 by 4. Yeah, that's a constant. So the determinant is 1. So that means it's non-singular. So there might be other things we need to that later that determinant will be useful for, even if it's 1 or 2, right? that could be different, but any determinant that's non-zero means the matrix is non-singular. Yeah, so there does exist an inverse. That's the takeaway. There does exist an inverse. It's rho equivalent to identity and all those other nice things we have. Yeah, rho equivalent to identity. AX equals 0 has only x equals 0 solution. All the other things that we've talked about. Okay. Yeah, so let's do a 4x4. Row equivalent means you can transform the matrix identity using elementary matrices. Correct. Yeah, so a row equivalent means there exists a sequence of elementary matrices multiply on the right that give you identity. So yeah, so each of those elementary matrices are row operations. Okay. What do you think we can do here? What column or row or column would be the easiest to work on? Well, row 3 has the most has no zeros, so I think column 2 might be the easiest. Yeah, because this one has 2 zeros. Now, from last time, what can we do to this matrix to make this even easier to make column 2 even easier to work with? So what did we do last time? What could we do to the matrix? Good, we can do row ops to make the determinant easy to calculate. Well, in this question, what row op do you think we could do? So remember, the goal is I want to get a lot of zeros, right? So if I do row 3 to row 3 minus row 1, I guess you mean row 1, then we get an extra 0. Question, type 3 operations, do they change how do they change the determinant? What do they do? They don't, yeah. Do not change the determinant. Does that do all the row ops do that? Only type 3. Right, so if you, I think it's safest to only work with type 3s when you want to do this nice trick. You can use other ones, but you have to be careful. Okay, so let's do row 3 minus row 1. Okay, so we have 2, 0, minus 3, and minus 2. Okay. Okay, so why is this so nice? Is because now when we do the cofactor expansion, the determinant will just be -1 to the, what is the power going to be? Right, 2 plus 1. What is the entry we're going to use? What entry? 1, 2. And what's the minor for what element? What's the M going to be? 1, 2. So everything is 1, 2. Okay, so -1 to the 1 plus 2 is -1. A1, 2 is 1. And let's look at M1, 2. Can someone read out to me M1, 2? What's the first row going to be? Yeah, 1, 1, 2. Second row. 2, -3, -2. And third row, 1, -1, 1. Okay. Okay, so, why choose coordinate 1, 2? Because all the other, so this is the prop. So if we're expanding on the second column, this what the determinant will look like this. K equals 1 to 4, -1 to the, let's see. So second column would be K2, determinant of M, K2, K plus 2. Does that make sense? Why this is expanding cofactor expansion about second column. Does that part make sense? So it's about the second column. Okay, so what's the only non-zero element in the second column? K equals 1, right? So all the other terms are 0, right? So what you're left with is -1 to the 1 plus 2, A1, 2, determinant of M1, 2, right? Oh, how do we choose before we got to this point? So first we saw column 2 has the most zeros, or most zeros, right? The most zeros. And then we saw, well, we could make this even easier for ourselves. We could do a row op to add even more zeros. Right? So now our new second column is a matrix with the same determinant because we used a type 3. Oh, it doesn't cause a problem. Why is that a problem? Yeah, I mean, I could keep it there, but the problem is it just gives you more work, correct? So remember, in each term of the sum, there are determinants you need to work out, right? So notice that in this, when we've eliminated to only one term, we only have one 3x3 to worry about. But if we had this one here in the beginning and we went straight to the cofactor expansion, there'd be 2 terms with 2 3x3s to work out. So the idea is that you can, so the more zeros that you can include, the less work you have to do. And so you can do the same thing even when we're here. To calculate this 3x3, well, there are no zeros there, so that's rough. But we can do row ops to give ourselves more zeros. Is that okay? Yeah, so for this last one, if you want to do row ops to make this easier, we could do 2 things, right? We could do row 3 minus row 1. And we could do row 2 minus 2 row 1. So those both will not change the determinant, but it would introduce more zeros into our matrix. So takeaway is zeros are nice for calculating determinants. Oh, in the beginning, yeah, that's what we did. We did row 3 minus row 1. But you could have, if you wanted to eliminate this entry, yeah, you could eliminate upwards if you wanted to. That's fine. We just chose, at least I chose to eliminate this entry because I think I feel like I'm more used to having ones at the top and then zeros on the way down. But yeah, you could have chosen either one to delete. Sure. So let's do those row ops. Okay, row 2 minus 2 row 1, so that's -5. Row 2 minus 2 row 1 is -6. Okay, row 3 minus row 1, -2. Row 3 minus row 1, -1. Okay, everyone see what we're doing? So again, just to kind of zoom out a bit, what we did was we looked at the second column and saw it had the most zeros. So if we calculate the determinant expanding on the second column, we'll have less work to do. So to do even more less work, we can do a row operation to make even more construct even more zeros in our matrix, in our column. So in this way, we only have really one non-zero cofactor, which is the cofactor on A12. So when doing the formula, we are left with finding the determinant of a 3 by 3. So we do the same thing. How do you find the determinant of 3 by 3? Well, if you do row ops, it makes finding the determinant a lot easier. Okay, so now we're down to here. So we've done row ops, and the determinant of this original 4 by 4 boils down to this 3 by 3 determinant. So how can we find the determinant of this 3 by 3? What column or row should we use? Column 1. Okay, so let's do that. And why is that nice? It's because now there's a 1 here, and the rest are 0. So there's only one term. So you have -1 to what's the power? One plus 1. What's the subscript? So I think it's easier to maybe talk about the subscripts. 1, 1. And then what's the minor 1, 1? So that's where the 1 plus 1 comes from. This is the sum of the coordinates. Yeah, so let's go back to, yeah, so even in our first example here, right? Going out the first column, we're summing the coordinates. And in our general, exactly. So everything is kind of handy, right? Everything will be the coordinates. So the -1 is the sum of the coordinate. A gets the coordinate, and the determinant is the minor is on the coordinate. Yeah, so this is 1. A11 is 1. And what is determinant of M11? What is the matrix M11? What's M11? Yep, -5, -6, -2, -1. So this is negative, so it's 5 minus 12, which is negative 7. So the whole thing is 7. Okay. All right, so any questions on that? So again, for 4x4, I really recommend using row operations. Otherwise, it's going to be a lot of work because then you'll have 2 or more 3x3s to worry about. But again, if you do row operations, you can only really deal with one 3x3. Oh, the absolute value sign is determinant. This is the same notation. It's just a little easier to write. So the matrix with the vertical line is determinant. Okay. Okay, so we'll talk about some proofs. So one is relating the determinant of a matrix to the determinant of its transpose. So here, why don't we do this? So what is the determinant of A? It is -1 to the 1 plus 1. Let's cofactor expand on row 1. So it would be the sum k equals 1 to n of -1 to the k plus 1. Let's do 1 plus k, a1k, determinant of m1k. So and let's think about the determinant of okay, so determinant of A transpose, if we do the same, and let's do cofactor expansion on column 1. So someone tell me what the coordinates would be if we're doing column instead of row. Okay, k plus 1. And what's the coordinates? K1, yeah. Okay, so if we write that out, we have, so let's write this one. Let's write this one out. We have, so when we plug in k equals 1, it's going to be 1 times a11, determinant of m11, and then it's going to be a minus sign. The signs will alternate. A12, determinant of m12, and then down to the last term, where k equals n. So it would be a1n. And we don't know what the sign is, depending on if it's even or odd. So let's say plus minus 1, and then the determinant of m1n. Oops. Okay, so if we if you think about M11 in the transpose of a matrix. So for example, if we have, let's do a 3 by 3. If n is even, then it would be a negative, right? If n is odd, then it'd be positive. Yeah, because they're adding 1. Well, this is, we're doing an arbitrary matrix right now, right? We don't know what the entries are, right? If you have a specific matrix, then it's great to work with row ups. But if it's some arbitrary matrix, then you don't know what row ups you need to use. Does that make sense? So if you have an actual matrix to work with, then row ups are great. But if you don't, then you kind of need to think more about matrix as a whole. Yeah. Okay, so let's think about how these minors behave when you transpose. So what is M11 for the first matrix without transposing? E, F, H, I. And then what about the transpose? What's M11 in the transpose? Yeah, E, H, F, I. So this is in the transpose. How are the determinants related? What's the determinant of M11? Equal, yeah. EI minus FH. And then determinant of M11 here is EI minus FH. So we can do that for the other ones. Just while we're here, let's do M12. DFGI, and let's do an M12 here is BHCI. So not quite the same. BI minus CH. So this one is EI. Oh, I'm sorry, what is this? This was supposed to be D. So DI minus FG. Now finally, let's do M13 determinant. So what would, what color? So M13 would be DEGH. And then could someone give me M13 for the transpose? Yep, BECF. Okay, so the determinant here is BF minus EC, and the determinant here is DH minus EG. So now when we do the determinant, we would sum up these entries, multiply by some value, right? So we would have A times EI minus FH, minus B times DI minus FG, and then plus C times DH minus EG. On the other hand, we have A times EI minus FH, and then minus D times BI minus CH, and then plus G times BF minus EC. So I won't do it all out, but it turns out that these are the same values. Things cancel and rearrange. So you can rearrange that one to the other. So I guess it comes out in these last two values that they rearrange to the same thing. If we think about that, if it works with a 3x3, so the term of the transpose in the 3x3 is the same as the original. So when we do these determinants, when we do these minors, right, for the 4x4, for example, since the determinants are the same, if we were to replace them with the transpose, and here, let me do a new page, just getting a little messy. So we have A11, and we saw that we can maybe, so this is induction, but we see it work for the 3x3, and we could see it maybe working for the 4x4 because the 4x4 is dependent on 3x3s. So yes, though we're guessing that it's going to be the same for n by n. So here's the proof of the guessing. A1n determinant of n1 2 transpose. Now, these are transpose elements, right? But I want these to be transpose. So, for example, what is A12 in the transpose? Where does A12 go when you transpose? So what does transpose mean again? Right. It's going to be A21, determinant of M. Now, values are the same. Those transpose well. And then, so if we flip-flop, these leading entries, the A11 to A11 transpose, A12, A21 transpose. Sorry, what is this? I have, something should be N, right? It's N1 transpose. So by manipulating the transpose, we get the determinant of A transpose, and this was the determinant of A. By manipulating the fact that we found that the determinant of the minors were the same. So it's kind of, I didn't realize it would involve induction, but it ended up involving induction, but sorry about that. But at any rate, the idea is we're using the case for the 3x3 that we proved, and we're expanding that to the n by n case. So another way of seeing this is that since cofactor expansion, it's kind of the general idea, cofactor expansion is the same on rows and columns. So you'd expect the transpose to behave the same. To have the same determinant. Anyway, so why is this useful? Because sometimes if we're doing some calculation, it may come useful later. But later we'll talk about determinant of a product. So knowing that the determinant of A is equal to the determinant of A transpose is useful. But just wanted to get through that fact. Okay, so here's something that's more tractable. The determinant of a diagonal, sorry, not diagonal, the determinant of a triangular matrix. So let's think about a triangular matrix. Let's think about what the determinant will be. Okay, so let's try cofactor expansion on the first row. Or rather the first column, that would make more sense, right? So in an upper triangular matrix, the first column is all zeros except for the leading entry, right? So can someone say what the determinant would be? The sum k equals 1 to n. And if I'm doing cofactor expansion on the first column, it would be a k1 determinant of mk1. So what would it be in this case? What is the only surviving term? A11. We have -1 to the 1 plus 1, A11, and determinant of M11. Okay, could someone read out M11? So what happens when you delete the first row and first column? What do you get? Right. So it starts out with A11 times determinant of A22 blah zeros, A33 blah zeros down to ANN, or not zero there. Okay, that looks pretty familiar, right? So what do you think you would do next? So now we have this determinant to deal with. So what's the determinant of that? We can do it again. Yeah, let's take the first column. So A11 times k equals 1 to, now it's gonna be n minus 1 because it's, well, maybe it's gonna be, let's do k equals 2 to n. There's still n minus 1 terms here, right? And then -1 to the k plus 2 and a k2 determinant of m22. I'm going to keep the notation from before so you don't get confused. Well, actually, why don't we just do anyway, so at any rate, it's going to be, it's always going to be 1, 1, right? So this negative is always going to be, -1 term is always going to be positive, right? So we have A1, 1, and the only surviving term is the first term, A2, 2. And we look at the determinant of what? Of M2, 2. Sorry, this is meant to be a K here. Okay, so what do you think happens? Let's keep going. What is the last thing you do? So it's A1, 1, A2, 2, and then you do it for the next time, and then it would be A3, 3. So what is the last thing you do? AN, yen. Yeah, so let's look at the last term. So at the very end, we would do A n minus 1, n minus 1 times the determinant of, and we know exactly what it is, n minus 1, n minus 1, n minus 1, n minus 1, and a, n. Oh, but this is 0, right? Okay, so, oh, sorry, this would be, I guess, no, this would be, I guess, n minus 2, right? Yeah, the very last thing would be some 2 by 2 matrix, and it would be a n minus 2 here, right? Okay, and then what is the determinant of this? Oh, y minus 1. So yeah, so at the very end here, it's a n minus 1, n minus 1, and a n minus 2, n minus 2. So the very last thing we do is we do this, and then we deleted that and looked at this matrix. There's zeros here, and whatever that is. So that part even doesn't even matter. So the very last determinant will be what? Just this product, right? Because this is 0. So a n minus 1, n minus 1, a n n. And that's just the product of the diagonal. Okay, so why is this so nice? Can someone say why this is so nice? Thinking about row operations? Yeah, if it is an upper triangular form, or you can do the same thing for lower triangular. So why is it so nice for any matrix? So why is this so nice? We can just do row ops, right? Yeah, we don't even need reducer echelon. That's the nice thing about it. All we need is any triangular form. We can put any matrix in triangle form. So this is really way back in 1.1, right? So you might have to be careful if you have to do row swaps or type 2 operations. You might have to be careful. But using type 3s, if you can put it in triangular form, then you just take the product of the diagonals. Okay, just a few other things I want to talk about, just problems you might see. Let's do like an algebra problem. Let's say, and this will pop up later in the course. Let's say you have the matrix 1 minus x, 2, 3, 4 minus x. I want to find the values of x that make the determinant 0. Okay, so what's the determinant? So it's the product of the diagonal. Okay, and then let's FOIL it out. How do you solve this equation? True, that would mean equals 6. But solving quadratics, yeah, simplify. What would this make? -2. How do you solve quadratics? Quadratic formula, okay. So that's negative b plus or minus b squared minus 4ac over 2a. Right, so it's 5 plus or minus square root. Yeah, very long time ago. And it's 4 times a times c over 2. It's 5 plus or minus 25 plus 8. So what is that? 33. Not a pretty number. Okay, so that's it, right? There's 2 values of x that make the determinant 0. So that's it. So, and just make sure you know how to factor this too, right? I mean, if this was factorable, that would be the other way of doing it, not using the quadratic formula. Okay, so be prepared for that in the homework. Just wanted to do that. And oh yeah, okay. So very last thing before we finish 2.1, let's think about. So we talked about this before, right? A matrix full of zeros with a row or column full of zeros must be singular. Can someone say why that's true again? Not based on what we've done today, based on other things we've talked about. Why is this true? We'll not think about the determinant. So the determinant, yeah, you can't get identity. So now by the determinant though, now it's obvious, right? Why is, with this new determinant definition, why is it obvious? Why would a row or column? Yeah, just pick that row. Just pick or cofactor expand on that row. Okay, so let's think about a consequence of that. So matrices with a row or a column full of zeros must be singular. Why is this true? If a matrix has 2 equal rows or 2 equal columns, then the matrix is singular. Why is that true? Row ops, good. Yeah, so let's say if row I is equal to row J, what row op would you use? a type 3, and the type 3 might be row I to row I minus row j, and this gives a 0 row. Okay, cool. So that's clear, right? All right, so here's the very surprising thing. And not surprising, but pretty powerful thing. If a row or a column in a matrix is a, let's see if you remember this term, linear combination of the other rows or columns, then the matrix is singular. Okay, all right, we haven't talked about linear combinations in a while, right? Does anybody remember what that is? So let's say I have a set of vectors, v1, v2, v3. Yeah, all possible combinations. So what are all possible combinations? Is something times the first plus something times the second plus something times the third, right? That is any linear combination. Okay, so now let's think about in rows of a matrix. What if row I is equal to, so let's say, except row I, to alpha k row k. That's a linear combination. Do you agree with that? So it's like alpha 1 row 1 plus alpha 2 row 2. I'm skipping over I, alpha I minus 1. And alpha n row n. You see how that's a linear combination expressed as a sum? So I'm saying if a row or column in a matrix is a linear combinations of the, let's just say, other rows or columns, then the matrix is singular. Can someone say why this is true? So it's a direct consequence of the thing we just said. I'll give you a hint. I'll give you the first row operation you can do. Well, then none of these rows are equal necessarily, but I'm saying that a linear combination of some of the rows is equal to another row. So like, let's say I have row 1, row I, row k. Saying that this row I is actually just like alpha 1 row 1 plus alpha 2 row 2, and then like alpha n row n. That's what I mean by linear combination. So based on what we just did before, the hint is I'm saying that you can get a 0 row out of this. If you have a row that's a linear combination of the other rows, then you can get a 0 row. I'll give you the first row operation you do. Let's do row 1 to row 1 minus alpha 1 row 1. Sorry, not row 1, row I. if this is row I, what is the new row I after the row operation doing this? What do you get? Not 0, you still have this other stuff, right? All you're doing is get rid of that one. You see that? Doing a row operation, and I'm taking away alpha 1, row 1. Nothing's becoming 0. I'm just, I'm doing that type 3 operation. Minus alpha 1, row 1. Is that clear? Yeah, that's what I mean. Let's take row 3 and do row 3 minus row 2. What do you get? One, one, one. So notice that this is row 1, row 2 plus row 3, or so row 2 plus row 1. You see that? And what the last thing you would do is row 3 to row 3 minus row 1. And then we get a 0 row. So do you see how row 3 is a linear combination of rows 1 and 2? So, okay, let's expand it out. There's a lot of other rows. So if you do this one step at a time, first do row I minus alpha 1, row 1, then do row I minus alpha 2, row 2, row I minus alpha 3, row 3. What happens if I do that all the way up to row n? This is exactly the same as this. You see the same? How they're the same? This is exactly the same as this. And this. In this case, the alpha 1 and 2 are 1. Yes, no? Become quiet. Does that mean you don't understand or you're tired? Right. I guess I'm tired processing. Okay, so let's say we have row 1, row 2, row n. Let's say one of the rows is A row 1 plus B row 2 plus, I don't know, Z row n. The idea is we can do several row ops. And let's say this is row I. We can do the row ops, row I to row I minus A row 1, do row I minus B row 2. And you could do that for every single term. Row I to row I minus Z row n. So if you do that for every single term, you can do row ops to zero out row I. Okay, that's it for 2.2. So Monday we'll do a review. The homework is due. I might give the solutions for 2.1 over the weekend, even though they're still due, but when you look at something, you look at the solutions. But okay, I'll start recording.